restart this. And now I'm live on YouTube. I think so. Perfect. Now I'm live on YouTube. Good. Okay, so now I'm live on YouTube. That's good. I'm also live on Twitch. That's also good. Yeah. And that means I can now begin. So, let us begin. Begin. So let me just let's put a message there, and let's put a message there. And I just need to look at this thing here. Okay, now we are set. So let's continue from where I left off last time. So off stream, I did some stuff. I created this function called inference, and what it does is it gives me an inference of anything that I want. So that's pretty good. For the main code, this was the entire main code which was already written. And then one really nice thing that I did for the revision code was I went to each of these cell blocks and I wrote this thing called percentage write file template data setup.py. So this was for the data for the data set. This was for the model builder. This was for the training loop, which I now call the engine, and this was for this was the main code, so nothing over here. But yeah, for the main code, it was write file template train.py. And what that basically does is by adding this line of code at the top, you can now convert your cell blocks into actual, what would I say, Python files. So you can see now I have Python files over here, which is pretty good. And the second thing that I did was added argument parsers. So now instead of hard coding the values over here, I can set some default values over here. And if I want to change them through the terminal when I'm running the code, I can do that as well. So I can just write Python, whoops. So an example code could be this one. I can just copy paste this, and then I can just delete this and delete this one as well, and then show you how the training works. So let me do there and just run that command. So I'm just running hidden units as 10, so that's the number of kernels as 10, and also the number of epochs as 10, but the default is 5. So we'll see that this argument is being overwritten. But other than that, everything remains the same. I could have chosen not to write this at all, and it would still make no difference, except for the learning rate. But yeah, just wanted to show that it still works. Okay, so that's loading right now and executing. So we will wait. So the first three loading is for the data loader. So it's like not the data loader, but the data set. It's like training the data set. It's training the data set right now. So we are gonna wait for this to complete. And now in this stream, I'm going to start implementing Alexnet. In the previous stream, it was more of a revision, but now today I'm going to actually implement the Alexnet. Yeah. I could add something very fun to do, which is while the training is being done, I can play some game. And once the entire thing gets completed, then I can switch back to it. That would be pretty fun to do. Yeah, I'll write this down. Okay, so the training is complete. Now, if we hit refresh, we will see we have our data set in the template folder, and we also have our model as well. And when we also run the inference, the predicted value was, or the predicted class was ankle boot, and the actual was also ankle boot. So it works. Perfect. Now let's begin with our stuff. So I will just leave this here, the main.ipynb file. I'll just delete this, and I will delete this as well, and I will delete the models folder, and inside here we will create our alexnet.ipynb file because we are going to do some testing. So let's bring out our research paper. We have two research paper for some reason. Do you want to save this? Yeah, sure, save it. Okay, and it closed both of them. Nice. Very, very, very nice. That's not good. Not good. Okay, let us open the research paper. All right. Um, we have the data set. So we'll start with the data set first. Um, or I can start with the easy stuff first, which is the model. Let's start with the model because it's more easier to do. So, we have this model, and we'll first look at what it is, and then we're basically going to use the more advanced version to actually do the coding. So what we have over here is a very complicated convolution neural network. And I'm going to see if there are any open source or online tools where I can create the CNN network so it's more easier and I don't have to look through this. So CNN visualization. Can I create my own model? Hmm. Nope. 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 I think there was like one, it was Neutron, I think, where I can basically design my um, uh, wait, I have to find one. Is there a tool online where I can create a visualization of the model of Alex of a CNN where I can specify the conf2d, relu, maxpool, etc. Yes. No. There we go. Leanet style. There we go. So this one is a little bit much more better in visualization. Um, yeah, I think I'm gonna go with this one. So for this particular model, right, we start with a 24 by 24 image. So the architecture, let's see how to use this. So we have this, this, this. What happens when I do? Okay, let's make it like that. Okay, okay. Okay, so we have an image of one channel by 224 by 224, and I think that's just telling you how much width you want. And then we apply our convolution. Um, so no, the first convolution layer filters the 224 by 224 by 3 image, so that's 3. So RGB image with 96 kernels of size 11 by 11 by 3. So you apply 96 by 96, and I can't show the kernel. Um, okay, screw it. Then I will just write it down. Um, you know what? This is becoming more annoying to do. So what I'm going to do instead is I'll just make the drawing, to be honest, because it's way more simpler. Uh, so let's do this, this, and let's Let's make this a little bit bigger. Super. Okay. So, let's begin. Oh yeah, I have to first of all fix this. Now it works. Okay, so let's start with the very basics. The image, right? So we have an image over here, and let's assume that we have 3 dimensions at first. So this is 3, so I can say that this is 3 by, and then the actual image is 224 by 224. We apply. So let's just label this. This is our image. We apply our kernel, and the kernel that we apply is why why is it asking me to stream together? I don't want to stream together. Okay. Yeah, where was I? So 224 by 224 image, and then let me open my research paper, and then there is 96 kernels of size 11 by 11. So we have one, this is the kernel, and then this is basically 96. So 96 by um, uh, size input image. So the first convolution layer filters the 224 by 224 by 3 input image with 96 kernels of size 11 by 11 by 3. How is it 3 dimensional? Maybe because I think they're assuming that this is 11 by 11. I think I did the calculation somewhere or not. Okay, I didn't do the calculation. And then when you do this, then what are they doing? So 48 by 48, which I think is 96 because they're splitting it up. So let me show you what I mean. Oops. Oh, oh. Yeah. So over here, what they're doing is um, they have split the uh, the 96 into 2 different convolution neural networks because they had a limitation of the GPU. So that's the reason why if you do like if you do um, for example 48 plus 48, that's 96. So that's 96 in total. And when you do this, you get an output image. And the output image that you get, so let me grab like a different color. So the output image that you get is, just a second, is what now? That is so you apply the first convolution, and then max you apply max pooling. The stride was 4, so we're here. Let me also write this down. So the stride is 4. Um, yeah, the stride should be 4. Uh, Let me read this. The first convolution layers filters 224 by 224 by 3 input image with 96 kernels of size 11 by 11 by 3 with a stride of 4 pixels. This is the distance between the receptive fields of the neighboring neurons in a kernel map. The second convolution layer takes as input the response normalized and pooled output of the first convolution layers. So, and pooled. So you do the pooling and your total um, uh, your image, I think, is 55. Yeah, 55 by 55. So the image is 55. This thing turns out to be oops, 55 by 55, and the amount of kernels that you have is 96 because this gets carried forward. So again, this is like 96. Why is it 55 by 55? We can use the formula, which is n plus 2p minus 1 divided by s. I think this was the formula. So your starting image is basically 224 plus, right now we can assume the pooling is 0. So you get minus 1 divided by s, which is 4. Wait, let me see what was the formula for this. CNN formula. Sorry. So let's delete that. The formula is n out equals to n in plus 2p minus k divided by s plus 1. So n over here is 224. This entire thing is 0 for now. Let's assume minus k. So minus k is how much? That's 96. Then you have divided by, sorry, 96 is not that. It's the kernel size. So minus 11 divided by the stride, which is 4, and then plus 1. So that will be 224 minus 11, that's this, divided by 4, that's this, plus 1 That's 54.25. And what they're doing is they've specified that it is um, over here as 55. So there are two ways of mitigating this problem. One solution is if we use padding, if we assume that there was some padding done. So um, we're going to assume that the image that they gave had stride 4 and and this is very important, the padding was 2 over here. And what that means is that we're basically adding 2 pixels around everywhere, so this 224 gets converted into an image of 227. And now if we do that, so instead of this, we get plus 4 minus 96, sorry, minus 11. And now when we calculate this, we get 224 plus 4 minus 11 divided by 4. Nope, didn't work. 24 plus 4 minus 11. Okay, so it's not 4. This should have worked. What mistake am I making? I'm making a mistake. Two two four plus 2 times 2 is 4 minus 11 . I'm making a mistake. I am making a mistake. What is the mistake that I'm making? Ah. Okay, so basically I was talking to Gemini and it said that if I don't add the padding, which is 2 to 4 minus 11 divided by 4 and then plus 1, sorry, and then plus 1, this is 54.25. and you're always taking like the floor. So this will not work because in the paper they said it's 55 by 55. So what you can do is if you do 2 to 4 plus 2 times the padding, which is 4, and then you minus um, the kernel, and then you divide it by 4, and then when you add 1, and now if you take the floor, then you get 55, which is what we wanted. So yeah, that's basically what they suggested. So I'm gonna go with this, and then you get a resulting image of 96 by 55 by 55. So that's number one. Then let's look at the other part. Then we apply max pooling. So we can just say pool. So this entire thing was convolution layer 1. Conv um, layer 1. This entire thing. Then we do max pooling of size. I think they're doing it of size 2. I could be wrong. Um, so you're never going to look at this because this is the number of channels. Um, so 55 by 55, if you divide that by 2, 55 divided by 2, that's 27, and you're taking the floor of that. So again, it's like a max pool of 2. Max pool 2, not I'm not talking about 2D over here, I'm talking about what I actually applied. So this is max pool 2, and resultant image that I get over here is oops, the purple one, 9. So this is still 96, but now this has decreased to um, this has decreased to uh, 27 by 27, and this is still 96. So that's the calculation that we've done so far. Um, and the number of channels are also increasing. Let me see why the number of channels are increasing. So technically, um, if we ignore this part and we just see from here to here, the number of channels are increasing from 3 to 128. 128. So this, wait, wait. The math is not mathing. It's 128. So tell me why things damn, I'm sleepy. So even in the official Alexnet implementation that they've done over here, They're using 64 channels. Then they do relu. Then they do kernel size as 3 and then kernel size stride as 2. The reason why they do this like 3 and 2 is because, okay, so sorry, you cannot see the screen. Let me bring it over here. So over here, they're basically doing conf 2D of 64. And then in max pool 2D, they're doing kernel size as 3 and stride as 2. So if we look over here, they do mention in point number here in 3.4 that they're applying overlapping pooling. And the reason why they're applying overlapping pooling is because you don't want to lose the details on the edges, um, and that you have a more smoother transition. So this is the entire explanation over here, like why do we need the overlapping pooling over here. So this is the example, and then you're like saying that if the stride and z is equals to the same, then what is the effect? And when you have s as smaller and z as bigger, so z is the um, z over here is the window size of the max pooling kernel, then um, you would say that um, it helps to achieve the spatial invariance, and then it's way better than the default one that you have. So that means that's why they're basically applying the 3 and 2. But what I don't understand is the 64. So they go for 64 and then they go for 192. So they go for 192 because of this. They go 64, which I'm guessing it's because of this. And then they have 384. Then they have 384. So I think this architecture is a little bit different. Um, they've used two GPUs. Yeah, um, I did notice this that they're using two GPUs. While I was reading it, someone suggested me that I could just combine this. So, for example, 48 by 48, and that would be 96. And then this 128 and 128 would be like combine 346 or 56 or something like that. But over here, it's half the amount of channels. That's why I'm getting confused. There should have been twice the number. So that's why I'm getting a little bit confused. Mm, okay, so I am now going to ask an LLM and also see if I can find some information. Why did you you have to calculate using the stride and padding? Yeah, so I did the calculation over here. Um, uh, but the thing is, like, when I'm calculating using the stride and padding, that's basically like giving me the dimension of the feature map, right? Which is um, this thing. So for example, if I have the image dimension of 224 by 224 and then I apply the entire calculation, that gives me the image dimension, the height and the width. But the number of channels that is dependent on the number of kernels that you're using. So what I mean by that is, if I can show the right, um, do, 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 do. Yeah. So over here, I mean, if you say this is 64, then this gets carried forward. There is no calculation involved. When you say 64 to 192, then you're basically saying that from this 64, you now have 192. That's it. That's how the number of channels are being calculated. My question right now is, like, they used two GPUs because at that time they had hardware constraints. Right now we don't have any hardware constraints. If we want, we can just merge this into one whole big network. So the number of channels should be like 48 plus 48, that should be 96. For the first layer, it shouldn't be 64. Okay. In the diagram you uploaded, you can see they do it in 46. Okay, single GPU. The modern Pytorch implementation is actually based on later one GPU version of the Alexnet released by the authors. Since modern GPUs, okay, why do they use 64? While the original 96 was effective, 64 is a power of 2, which is much more computationally efficient. Let me see if I can find their this modern version. Uh, can you link me to the 64 filter 1 GPU? But yeah. Okay, so this is one weird trick for parallelizing convolution neural networks. Uh, oh my God, it's I had it open over here already. So this, I think, is where they're basically describing this entire like 96 thing. Um, so let me look at the PDF over here. Ba, 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 ba. Do they say it's 64 over here? Let me see. 64. Ah, here we go. In detail, the single column model has 64, 192, 384, 384, and 256. Okay, so this is where they're basically explaining this thing. Makes sense. Um, yeah. So technically, I should not follow this entire thing. Instead, I should follow this research paper, and I have to read this entire research paper to see what was so different and the one weird trick of parallelization. But for some, that's why lol. Yeah. um, but for simplicity, what we can do is we can just go with the Alexnet implementation that they have mentioned on their GitHub page, which is pretty easy to follow along, to be honest. It's like they say over here. So we have kernel size as 11, stride is 4, padding as 2. Okay. Um, the kernel size is 5, and then padding is 2. I think this remains same. If they mention it, yeah. So they're not changing the kernels, I think. So 5, and then there is 3, and then there's another 3, and then there's another 3. So it's 11, 5, 3, 3, 3. So let's see if this is also followed in the implementation, the modern implementation as well. So we have 11, 5, 3, 3, 3. Okay, so that checks out. Um, Also, I think in the newer version, I think they also mention about the padding as well. So where is it? Let's see if they talk about padding. Not here. But when I was chatting with the LLM, I'm basically using Gemini. It did tell me that they made some mathematical calculation errors. So if you don't add the padding, this entire architecture doesn't work. So the way how you do the padding is for the first layer you add padding as 2, and for the other layers you add padding as 1. And that's also what is also seen over here as well, that they start with 2, 2, and then they do 1, 1, 1, 1 to like make it match or make it work. So the next thing that I need to figure out is why did they use adaptive average pooling and not the standard pooling method? That's one thing. I also need to see what is this thing, which is the log API usage once. I'm curious about that. And yeah, I think that's pretty much it. Um, this is where they're basically like importing the weights. So we'll see. Okay, let's write the bare bone of the network. Let me change the screen to this one. And let's make the screen bigger. Okay. By the way, how was your day today, Duchi, if I pronounced it correctly? Uh, there we go. Okay, and VS Code. Okay, good howdy. Import torch. Let's make this a little bit bigger. So I've gone ahead and I have created a template. So technically, no, I should make this again. Okay, so import torch, and then we can say import torch nn as nn, and then we can create our Alexnet class. So Alexnet, and then we basically inherit the nn.module class over here. Then we define our arguments, which is the number of classes that we want to classify, which is going to be of type integer, and the default value is 1000 classes. Maybe we'll reduce this to 10 classes. So I think they're using ImageNet, and we can reduce the amount of classes to our needs. Maybe like add one last layer and then apply transfer learning. The dropout is going to be float, which they have mentioned that they kept it to 0.5. They said in the paper that 0.5 was during the training, so they were calculating a probability of dropout as 0.5, and then when you're doing the inference, they just multiply it by 0.5. And I think this is basically taken care by Pytorch on their end, so we don't have to implement this, and we're not returning. I think it's better that we return. Where is my model builder? Yeah, we return nothing. We return nothing. So a really good resource that I'm using is, all credits goes to this guy. Um, this is a research, not a research, but a really nice blog post that I found about How to Learn Pytorch for Deep Learning, Zero to Mastery. I forgot his name, who wrote this, but this is a really nice resource, and I'm following their PyTorch going modular approach, where what you do is you write your entire code in sort of like different py files. So it has this separation of concerns thing, and what's really nice is you can define your arguments through the terminal, and your like hyperparameters, like, hey, Python train.py, this is the model that I want to run, this is the batch size. So really, really professional. And they also took this inspiration from the PyTorch GitHub page. So I'm going to try to implement uh, or my best attempt at implementing best practices when I'm trying to recreate Alexnet. So okay, then we do super dot init because we need to, yeah, let's go. We have to do call the initialization of the parent class, and then we can start. So we can start with our first block. So let's say that this is self.conf layer 1. This is going to be a sequential, and we will have nn.conf2d. Yeah, with 3 channels. So we're assuming that we have an RGB image, and I can just take this doc string. Uh, so creates Alexnet architecture. Alexnet architecture. We can give add description later, and then we can define the arguments. So we can define the number of classes as an integer, indicating the number of um, classes to be classified. We can define the dropout as a float, indicating the dropout rate. And I think that's pretty much it. Yeah. So a really good thing about doc strings is that when you're actually creating your network, so I can say model equals to AlexNet, and once it compiles, then when you hover over it, it tells you that, hey, you, oh, AlexBet, AlexNet, AlexNet architecture. So when you hover over it, it tells you like, hey, you're creating the AlexNet architecture, and then it tells you all of the things as well, like, hey, this is the argument number of classes. So it's always really nice to also keep updating your doc strings in case that if you ever forget what these particular variables stands for, you can just hover over it and remember. Okay, so let's do a quick revision. That is, the first thing that we need to tell is the input channels. So we say input channels as 3 because it's an RGB image. We set our output channels as 64. Then we have the kernel size. So kernel size, that's 11. And then we have the stride as 4. And we have the padding as 2. So that is our first layer. Then we apply ReLU because we do not want to overfit. We do not want saturation when it's computing the gradients. And also it helps us to train faster. And then we have in place, which they have set to true. But why? in place Pytorch. In place is an argument used in different functions. But since the ReLU function is applied element-wise, there is no need to specify input or the output dimensions. The argument in place determines how the function treats the input. If input is set to true, then the input is replaced by the output in the memory. Okay. So let me just take this. Alright, so you have a random float value, you have another random float value, you add them, and then okay, so this is the difference. It's updating the value of x as well. But how does it help us in ReLU? So it's memory efficiency, standard ReLU. In place equals to false, the Pytorch keeps the origin input tensor x and creates a second tensor to store the output y equals to max 0 and x. For large models like Alexnet, this effectively doubles the memory required for that specific layer's activations. Okay, so it's kind of like a memory trick as well. This reduces the memory footprint during the forward pass. Okay. To calculate gradients, Pytorch often needs the original input values of a layer. If a subsequent layer needs those original values to compute its own gradient, but you've already overwritten them with in place equals to true, the code will crash. Okay. So in short, you shouldn't use this blindly. Um, what I found is, let me see if I can bring that over there. So yeah, similarly, like what we saw over here, I mean, this is like a benefit that you don't have to like the memory is not creating another another tensor or another variable to store this value. You're just storing the value in the original variable, so that's like memory efficient in one way. Um, but you have to be careful because if you want to apply an operation where you're calculating the gradients of the original input values of a layer, then you don't have that value because you overwrit your variable. You have already overwritten them. So in our case, it doesn't really matter because we're not using the previous value for, I mean, it's not important that if it gets overwritten. But if for some reason, if you are doing some sort of like calculation and you require the previous original value, then you would do this as in place equals to false. But in our case, that will add as like an optimization trick. So we'll set this to true. Okay. And yeah, if you don't understand anything or you're also confused, you can like join in and then we can have a conversation. That would be also fun. Maybe I might be going offside or in the wrong direction. But that would be fun. Okay, let's continue. n.maxpool 2D. This is kernel size as 2 and the padding, not the padding. the stride as 2. Kernel size should be more than this. Yeah, should be more. Um, and that's our first layer. Then we do the second layer. So conf layer 2 equals to. Okay, so they're applying relu separately. Okay, we can do that. We can do it like this. Doesn't matter. Then we do the second, which will be almost the same. So this is conf layer 2. In channels will be now 64. Then this gets to 192. The kernel size will be 5. They haven't mentioned anything about the stride, so I think it's going to be 4 by default, and padding will be 2 again. So that's this one done. 64, 192, 5 and 2. That's good. And then we do nn.value in place, and then we do the max pool. And then we copy this again, paste this, and we do this as 3. Okay. Oh, I just saw this, by the way, that you followed me. Thank you for the follow. Um, nope, nope, nope. There, there, there. Okay. Um, yeah. I don't know if you are still here, Ducci, but thank you for the follow. You could be my first follower, but yeah, thank you so much for it. Means a lot. All right. Where was I? Yes, I was creating the network. So this is 64, 192, 5, and 2. Then we have our third layer. So the first layer, the second layer, the third layer. So this is now 192, 384. Yeah. And so my journey begins on Twitch with my first follower. Okay, 384 kernel as 3, and then all of the rest of this is 1. Place 2. Oh, they're not applying max pooling here. So they apply max pooling on the first one, on the second one. Then we have these 2. Then we have another one and another one. So yeah, I can also talk a little bit while I'm coding this out, because technically I'm just copy pasting the values from the paper. Yeah, I would ask one thing, which is, are you in school, college, university, job? Ugh, 384, and the out channels then gets to 256. The kernel size is 3, 1. This should match. Yes, 256. Then we have 256 by 256. Also, if you don't feel comfortable in sharing anything, you don't have to. But yeah, I was uh, just trying to initiate a small talk. Okay. Um, so we have that done, and then we have the max pool 2D as again the same thing as this. Okay, let me just do a quick a quick, oh, I still have more after this. So hmm, okay. All right. Uh Dropout. Combining the predictions of many different models is very successful. Yada yada yada. Yada yada yada. This technique reduces complex co-adaptations of the neuron since a neuron cannot rely on this. It is therefore forced to learn this. Uh, we use the dropout in the first two fully connected layers of figure 2. Okay, this is a little bit different. Let me look at the modern architecture, because they say in over here that they're applying the dropout only in the classifier layer. They didn't apply the dropout in the convolution layer. So let me see, why is that the case? Maybe I can get some hints. Uh, Drop out, nothing. The original paper uses this, but the modern PyTorch only applies it at the classifier layer. Why? Why, why, why? Why, why, why? Why are you like this? Why? To be honest, I did kind of choose a very wrong paper to start with, because it's a very outdated paper. The reason why I started with this architecture was because this is like where computer vision basically starts from. And this is like the most easiest paper to start with. And then I was like thinking I do this, and then I do another paper and another paper until I reach the LLMs or the transformers, replicating it by paper, because that's like a really good practice, um, and really useful thing to have when you're pursuing your career in AI. But turns out this paper is crap in not in its time. In its time, it was the most golden paper. But when you are replicating it to our modern way, there's a lot of discrepancies. Okay. It's easy to get this impression, but I have some good news. Modern PyTorch implementations actually do keep the dropout layers in the fully connected classifier section. Yeah, but did I read that wrong? In the first two fully connected layers. Oh my god, I read that wrong. Yeah, we're basically doing the same thing. I for some reason I assumed that they were talking about because they said the first two. You can get a lot of information on it. It is worth, yeah, it is worth it. I got confused because it said the first two layers, so I assumed that they were talking about the convolution layer, but they do say the first two fully connected layers, which is technically these layers, and these are the classifier layers. So, I mean, we're still implementing it correctly. So, yeah, my bad. Let's continue. Da-da-da. And I don't know how many Chrome tabs now. Let's close this one. Let's close this one. Let's close this one. What is this? Okay, this is the one. Okay. Getting back to the implementation. Let's put this down here so I can use this as reference. Okay. First convolution there. This is done. This is done. This is done. This is done. Then they use adaptive average pooling. So self dot average pool, we'll call this average pool. This is nn dot adaptive average pool of 6 by 6. Then we create our classifier. You don't have to input the result of the max pool layer directly into the next convolution layer. What do you mean by that? Like over here? Or do you mean by the average pool? The result data is biased. Um, do you mean by um in general the max pooling layers or the adaptive one? And yeah. Yes. So I think you disconnected or something, but what I was asking was you said you don't have to input the result of the max pool layer. Okay, you are talking about the max pool layer directly into the next convolution layer. The result data is biased. Hmm. But why? I do not under. What do you mean by the result data is biased? Ah, never mind. I just saw it is in it. Yeah. I haven't created the forward pass yet. I'm just building the skeleton right now. So sequential. The way how they implement it is pretty. I mean, it's better. um, because then I have to like write this as like this, which is uh passing it to the first convolution block and then passing it to the second convolution block, whatever. Um, maybe it's better that I add this entire thing over here, and it's better that I write this as block, because I think that is way, 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 way better than me having to write all of that down. So that's da 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 on ta, and then similarly z z z z z z z z z, because I have OCD and I would like to have pretty. Pom, 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 pom. I just wanted to tell you about the normalization layer. Actually, batch norm has two in it as well. Yeah, you like adding like batch normalization over here, right? Do you mean by that? Yep. Yeah, yeah, yeah. That I think it's like batch. What was it again? NN dot batch norm. Yeah, like this, and then you can add whatever normalization you want. Yeah, in the deep learning like community, it's like way better. I mean, in every single they use LRN layer though. Yes. So I was not I was talking with Jem and I about this. And I did this entire understanding of what the LRN layer is, understanding the mathematics, whatever. Um, they say over here that where is it? There it is. They say over here that ReLUs have a desirable property that they do not require input normalization to prevent them from saturating, but they still implemented a normalization technique like local response, which was acting as a brightness normalization. So I asked this to Gemini and I was like, hey, the implementation which is given on Pytorch, that doesn't mention anything about this. So what's about that? And they said, or what Gemini said was layer RNN was a pretty old method. And the claim that they made was that it actually improves the performance. It wasn't like a very drastic performance, and even if you remove it, it's not a big deal. So you can remove LRN, and it's better to use batch normalization because that's way better in the recent community because that's basically being used everywhere. So I was like, oh, if I would have only known about this before, I wouldn't have gone into the entire details, but it was still a really nice refresher on my mathematical. It is kinds of prototype of batch norm. Oh, I see. That is where it started. The stems, the root. Wait, let me turn on some lights. I have some lights now. Let us continue, continue, continue. Ba, ba, ba. So I'm just adding a comma in if I just feel like adding the batch norm at the very end. If I'm not satisfied with the results, I can just quickly do that as well. And a comma there. Perfect. So we have very nice blocks, and we can now continue. So the average pool is the adaptive average pool. Again, I have to read on this. Why am I using this? Or why did they use adaptive pool? But before that, I'll just quickly write the classifier block. So you use a dropout where the rate is now dropout, which was here. We then add the linear layer as 256 by 6 by 6. And we are connecting that to 496. So this is, I think, equivalent to nn.flatten, if I'm not wrong. And I think you can do nn.flatten, and if you want to see what this basically is, then a really good trick is you basically know what's coming from the previous layer, right? So that's hidden units. So we know that this is going to be 6 by 6, but this 256, let's assume that we don't know what this is. And then what we can do is we can run like a forward pass, and then it will tell you that, hey, it's expecting this, like this value. So then you can just write 256 with that. I'll show what I mean by this thing. I didn't know about this. It's pretty useful. Okay, nn.relu, and then we have in place equals to true again. And then, like they said, 2 times. In the first connected layer and in the second connected layer, you have your dropout as p equals to your dropout. And then you have the linear layer as 4096, 4096. And then another nn.relu. To be honest, I will separate this out so it's more easier for me. Not for me, but it's more easier to compare. I know I didn't make any sense with that last sentence, but what I mean is like how I was separating this entire thing into like convolution blocks. So I can like just bring this thing and be like, hey, where's the architecture? This is first convolution block. This is second convolution block. This is third. Right now, this entire thing is like jumbled up into one classifier. So I'm going to split that as well because I want to do it. So I will do it. So like that. FC2. This should be nn.sequential. And then over here, self.classifier, classifier equals to nn.sequential. Just put that there. Why am I getting an error? Because I didn't put an equals to sign. Okay, that's better. The rough skeleton is now done. But let me first see what was nn. Adaptive. Why did they use adaptive average pool 2D? I will be right back in 2 minutes. I just need to refill my water bottle. I'll come back. All right, getting back. Um, where was I? Where was I? Yes, adaptive average pooling. The original paper, the 2012 model, was strictly designed for a fixed input size of 224 by 224, effectively 227 by 227, because when you apply the padding, then it gets converted into that. If you fed it a different image size, the spatial dimensions at the end of the convolution stack would change, causing the code to crash when it reached the fully connected layers. The modern Pytorch adaptive average pooling 2D allows you to feed the model images of various sizes, 256 by 256 or 300 by 300. It dynamically calculates the necessary stride and the kernel size to ensure that the output is always 6 by 6. So the classifier part of the Alexnet expects a flattened input of exactly 256 by 256 times 6 by 6. Without the adaptive pooling, if the convolution output was 7 by 7 instead of 6 by 6, then the flattened input would be 12,000. Okay. So it's like a sort of like a resizer over here. Thank you. I am back. Yes. All right. So, yeah, the rough skeleton is now complete. What do I want next? Next, the forward. Define forward. This will be self. This will be an x, 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 which will be a torch tensor because we do everything in torch tensor, torch.tensor. And we will return a tensor. So this will be our overall, wait, this should be with a capital T. Um, so this will return us the forward value when we do the forward pass. So x equals to, here it goes. So we put that into the first convolution block, and I can just copy this, which is, it's would be nice to also see what the shape is. So the output shape after the first convolution block is this, and then we can just do this as da-da, 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 2, 3, 4, 5. And then we can do FC1, FC2, and the classifier. In the original implementation, they do it like this. Features, average pool, flatten, done. I mean, it's way more easier. Oh, so they are flattening it, but they're flattening it over here. So I will add the flatten layer maybe here then. And they did it because they didn't do that much abstraction like I did. It's fair enough. Doesn't make any difference, to be honest. So this is 1, this is 2, this is 3, this is 4, this is 5, and then they do the average pool. So, and then after the average pool, they're passing it in the flatten. Where is my flatten? There it is, my flatten layer. Then I do FC1. Then I do my FC2. And then I do my classifier. 2, 3, 4, 5. Average pool block. After my fully connected layer 1 block. The second one. And over here we can say this as What classifier block? Okay, that's done. Now we create the model. Model equals to the Alexnet. Let's assume the classes are still 1000. I think I can just call it like this. And then I can create a random tensor, um, which I should have it. Yeah, 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 yeah. Do I have it? No. Um, let's say random tensor equals to torch dot random, and then I can give my size. So the size that it is expecting is 224 by 224, and with 3 channels, so 3, and um random tensor, yep, dot shape, so that's this, and then we can do dot unsqueeze 0. This will add the batch value, the batch size thing, and then we do the forward pass, which is model dot forward, and then we pass in our random tensor, and it crashed. Why did it crash? 256 by 256 and 9216. It crashed here. So this worked, this worked. Is it because of the flattening that I did incorrect over here? Nine two one six. So 256 times 36. Uh, mm, 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 mm. Pretty sure this won't do anything. Yeah. So this is this thing. And it worked. Wow. Why did it work? I just removed the 256. Uh, and it worked? Why? Let's understand. The crash is happening because of two separate issues in your testing code, patch dimensions and how nn.flatten interacts with them. When you created the random tensor torch.rand 3 by 224 by 224, you created a 3D tensor of channels, height and width. Pytorch layers expect 4D tensor. Did I not pass? There we go. Now 256 will work. There we go. So it worked. Okay. So what happened was when I use nn.flatten inside FC1, it flattened the tensor starting from the second dimension. So if my input is 1 by 256 6 by 6, nn.flatten would convert this thing into 1 by 9216. So it just multiplies all of this thing. And then my linear layer, so nn.linear layer, this is where I said um, as 36, 36 by 4096. I'm right now trying to understand, like, by adding this patch dimension, how did all of the maths get fixed? So what's the difference when I add the batch dimension, that is use a 4D tensor in the model versus a 3D tensor? Pretty slow on YouTube. So oh 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 oh. Okay, so what happened was when I didn't added this batch dimension, it saw this tensor as 3 by 224 by 224, and it assumed that there are three batches of grayscale and 224 by 224. So that messed up with the calculation a little bit. And um, when I was doing, I mean, I was passing the entire um, thing without this. So when I do this, you can see it had only three tensors, and that it was expecting this 256 by 6 by 6 thing, um, which is like 256 to um because what flattening does is it starts with dimension 1, which is this, and then it just multiplies everything. So what was happening was over here when I run this, this works because it's expecting 6 by 6 after this, because that's what flattening is doing. So it didn't flatten uh, this part of the tensor, which is why when I removed 256 it was working. But when I add this unsqueeze thing, which is the right way of doing it, because you always require a batch, um, unsqueeze as 0. Then now when you apply flattening, it starts with dimension 1 by default and expecting 256 times 6 by 6. And that's why we added this 256 over here, the magical number, which I was saying, like, why do we do this forward pass? And it works. In short, the mistake that I made was I didn't add this unsqueeze thing. Always add unsqueeze. It's basically the the main gist. Always add batch size. Perfect. So the model is ready. Um, we now have to write the rest of the code. I think um, in terms of like the training loop, um, I am applying cross entropy loss because they do not mention the loss function over here, or do they mention it? Where is it? Nope. They don't mention which loss function they use, so we can use cross entropy loss for um, our loss function, and then we can use our evaluation metric as softmax, right? Softmax. Yeah. No, wait, I'm confusing. Sorry. No, no, no. Um, softmax something else. Yeah, so we can basically use cross entropy loss, and then we can evaluate it. I think this previous code that I wrote for tiny VGG will work. I don't have to change anything over here. For optimizer, we'll just use Atom optimizer. It will still work. But what I do want to change would be the data loader part. So I need to see how to load data. So my goal right now would be to grab some data set, train it on this rough skeleton, get the answer, hoping that we get some good, decent results. And after that, there are some stuff that I would like to keep. So let me grab my sticky notes and add them to my to-do list thing. So it's basically updating right now. I would like to track all of my experiments. So for that, I'll be using, I forgot its name. Yeah, VanDB, weights and biases. I'll be using that. Um, the second thing would be, so let me write this down. Use VanDB, weights and biases to track um, model performance. That's one thing that I want to do. The second thing is I also want to understand where is it again? Da, 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 da. Oh, it's over here. I also want to understand these other stuff, the log API usage. I think this is related to Pytorch. I mean, like how you're going to be using Alexnet to call it in your code. Um, this entire thing on how they're basically setting the weights. Then we have um, this part as well. To be honest, um, I am good with PyTorch, but I'm not too good. Sorry, I mean, I am good with Python, but not too good with Python. So some stuff that I always saw in like these libraries and these other stuff was KW arguments. I never knew what these were. So I want to understand what these mean. And also decorators. I think I've used decorators when I was writing some backend code using either Flask or Fast API, but I also want to like understand how to use decorators as well. So understand the original code provided by Pytorch. 100% completion. Completion. Okay, so I'm gonna take a small break. I mean, I'm still here, and I'm just gonna breathe before I continue re-implementing the dataset part, and then training the model, and then actually seeing that does this actually work or not? How good was our replication? I highly recommend you use other layer and check performance changes in the model. What do you mean by the other layer? Like importing this entire thing from PyTorch? Yeah. For example, Xavier init to the other, batch norm to instance norm. Okay, so like, wait, I think I've read this before. The Xavier int. It's like another uh, remove dropout. Okay, Xavier initialization. Yeah, I remember reading about this in my master's. A little bit about this. Replace average pool to softmax. Okay. Then I think I'll just write your recommendations down over here because these all comes in like the performance part of the model. So I can just play around with this, which is like you said, um, remove like change average pool to softmax, removing the dropout, batch norm to instance norm, playing around with these, and also the Xavier. So let me write this down. So Xavier init. I can also, I mean, not right now because I don't know if I've set up my GitHub right now because this is a new machine that I'm using. But yeah, later onwards, I'll add these down in my GitHub issues so it's more easier to like track them, or I'll create a project and then I can like be like, hey, I did this or I implemented this, whatever. But yeah, good recommendations. I'll do check these out as well. So batch norm to instance normalization. Then we have remove dropout any effect. Let's make this like that. Xavier batch norm to instance norm. Remove the dropout and the replacing the average pooling to softmax. Okay. All right. Yeah. So, yeah, just taking a small break, then I'll continue. So there's I don't know if you noticed this, but there is the title of my stream says reading AI research papers and software development. So there are like two different projects that I'm working on right now, which is like practice wise. So the first one is this research paper, which I'm doing, like trying to implement research papers, understanding the mathematics. And the other one is like implementing AI models into a product. So in the other project, so you'll see that I'm like bouncing around with both of them. Sometimes I'm doing this research thing, or sometimes I'll be doing that thing as well. So for the other one, basically I'm trying to implement um, a scalable application where you're basically using an ML model. So it's a very simple ML model. Like for example, on the Iris dataset, the second project doesn't really care about like how good the model is. The second project is more about, hey, in terms of like software engineering, how do you make an ML applied application? So when you're talking about software development, you're talking about, is the application scalable? Is it robust? Is it available? Right? When there are like 100 users um, appearing on the website, is it still responsive or not? So yeah, that's basically what I'll be doing in that one. Yep. So yeah. And the thing is, like, I'm trying to do it in the most free way possible. So, like, usually you can do scalability very easily using AWS, but then you have to pay AWS, and I don't want to spend money on AWS. So my goal with the other project is that if you have a powerful machine, unfortunately, you have to have some compromise. So um, basically, everything will be running locally on the computer. So other people will be accessing my computer, and then um, basically we're going to be creating scalability locally on the PC. So that basically means I have to learn how to use Docker, Kubernetes, and other stuff as well. But it's going to be fun. So let's see how that goes. All right. Um, yeah, thank you for your kind words. Um, it's actually really motivating to um, work on these things when you have someone to talk with. Makes a really big difference. So yeah, thanks for hanging out and joining me in this session. It depends, like model, like it differs, right? Like making your own model, um, how good you want your model to be. So that's why I'm like doing the research part, right? I'm developing my skills on how to create a model. So that's one skill that you should know, right? The more you implement this, the more you get to know, okay, how you make your own model. What are like really good techniques. For example, batch normalization, not batch normalization, but like how they were using layer response normalization, which was basically inspired from biology, and then they converted that logic through mathematical means. They use annealing method way back in gradient descent, which is inspired from physics. You have diffusion models, which is basically also inspired from physics. So how do you understand the mathematics of these things? How do you understand the probabilistic models? And then once you have enough knowledge about these mathematical skills, then you can easily read research papers, you can reproduce research papers, and then you can also like create your own models. But what I've found is a lot of the people, when they're reading research papers, they get scared from the mathematics. Me personally, I didn't have a really strong maths background, so I will be revising my maths over and over again. This includes statistics, probability. I think those two are the most important ones. If I don't understand anything in the research paper, and yeah, every junior AI are. I mean, I myself am a junior AI engineer. I mean, I'm just starting my career, so every junior AI engineer that I've met, they all are scared of research papers, and they always have the same question: how do I convert the mathematics in the research paper into code? So that's also like a skill that I'm trying to learn, which helps me to like separate out from other people. Okay, let's continue. I think this was ImageNet. Yeah, it was ImageNet. I see that you also have some experience in AI because you are giving me some very good suggestions. Do I have to download ImageNet? Does Torch Vision doesn't provide? Doesn't Torch Vision provide ImageNet? Do I have to? I have to download, but I don't want to download the entire thing. I want to download a subset of it. I built the Alexnet from scratch a couple of years ago. Oh, nice. Did you also do it with a single GPU or did you do it with the double GPU? And did you um like created it from pure Python? Or did you use some sort of like abstraction like PyTorch or TensorFlow, like how I'm creating these blocks stuff? Single due to no money. Yeah. Yeah. I mean, it's even more expensive now to get um double GPUs in this economy, man. Thanks to generative AI. Let me see. Because they did. Where's my? tensor for using only auto diff operations. I've not used um, TensorFlow that much, like very little, very basic. Let me read what this was. Auto differentiation engine from scratch. So I am assuming, I could be wrong, just from what it means. You didn't implement it a differentiation. It's almost the same as Pytorch. Okay, all right. I was just gonna say that maybe you did all of the stuff like from scratch, but you didn't want it to write the differentiation part, so the differentiation part was abstracted, and you used that instead. Uh, mm, technically, sure, why not? Um, I'll use a different data source. Should I? Because the ImageNet, uh, the most popular version of this is ImageNet, created by Jeremy Howard Fast.ai. It is a subset of 10, easily classified. 1.5 GB. Okay, sure. I'll download this one. Uh, do, 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 do. So we are now downloading the dataset in the meanwhile. And um, I have to create the data loader model. Uh, data loader. To be honest, I'll just reuse this. So training directory, I'll specify what's the training directory. I'll specify what is the test directory. Um, transform.compose. Where's my train.py? Um, yeah, because I didn't use it over here. 1 second. For example, convolution layers have to be built using dynamic programming in order to reduce operating time. Yes, 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 yes. Yes, that's like I think one of the reasons why PyTorch is way better than Keras. And then, okay, so auto differentiation allows you to do that in TensorFlow. Okay, understandable. Do 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 do. Sample usage. Do I have my sample usage over here? I do have it. So my training directory, my testing directory, and my transform. And my transform. Perfect. So I don't have to implement that. as well, which will be of type transform.compose. Yep, I can use this. Da, da, da. And then I can just write it like this. Okay, did it download? Nope. And I have a very bad download speed. It's downloading. Um, so uh, okay. So basically, I was just asking like, hey, like Gemini to like tell me a smaller version of ImageNet because the original ImageNet is like 65 GB, I think. No, it's 138 GB and 6.3 GB for only the validation dataset. So I was like, okay, I'm not going to install or download all of that. Give me a smaller one with only 10 classes. So it told me that, hey, you have ImageNet. So it's like, so this is the spelling. Yeah, blah, blah, blah. What am I doing? So it's this one, ImageNet. Um, and it suggested me some transformations. So the transformations that it suggested me was this one, and it says that this is the Alexnet standard transforms. So it says random resize crop, random horizontal flip, and then normalization. Um, to be honest, like these three do make sense because they're also mentioned in the research paper. Um, which was here. So they say that the first two data augmentation consist of horizontal reflections. This increases the size of 22048. Um, and the other one that they used was PCA. But then I asked Gemini, why shouldn't I use this? And apparently, this is computationally very expensive to do. And this is not done that much. Instead, what you can do is you can use color jitters as transformation, um, which is more lightweight and can like almost give you the same result. Hello, Sami. How are you doing? Um, I do want to see where do they mention the means, like the normalization of the mean and the standard deviation. Uh, so horizontal flip. Yeah. Let us see. Let us see what is happening. Transforms dot normalize. I wish I can be a hard worker like you. Well, um, to be honest, I even don't know if I am a hard worker guy. I'm just, yeah, just the job market's so bad right now that I have to learn these things. Otherwise, I don't think I'm gonna survive in the AI world, how fast it's progressing. Um, but yeah, I hope so too. And I believe in you that one day you will be even more hardworking than me. Yes. All right. Um, let's continue. Is math mandatory in AI and ML? Yes and no. So, um, if you're starting out, so okay, let me like give you a very easy answer to this. When you're starting out in AI, a lot of the companies right now require you to just integrate AI into their product. They really don't care how the AI is working, they just want results. So, what you can do is you can import libraries which have already done the heavy lifting of designing the AI and the ML part and the models part and whatever, and you just use them in your um, application. Simple as that. So those types of AI people are called like AI engineers or ML engineers. It changes from company to company. Um, so their part is just to like implement or to make it um, application based. Then there's the research side of AI, which is people who are designing the models, who are like writing research papers. So down the line, when you look for higher paying jobs, you'll find that people who have research experience, people who have published papers in very nice conferences, they have higher priority and importance to people who can implement these stuff because like these are like two different sets of like skills. One is like software engineering skills and the other one is the mathematical skills. So when you're starting out your career in AI or in ML, you don't require heavy maths. You can do it very easily. I mean, you can get away with it. But if you think about pursuing your career in this field, then sometime, maybe when you're doing your masters or when you're doing your research, it will come back to you and it will bite you again and again and again. And it will require you to have strong mathematical skills. So that's the answer. When you're starting out, no, but if you want to do it professionally and you want to do it seriously, just be an AI engineer, then yes. Yeah, I won't sugarcoat it. Okay, what was I doing? Normalization. That's good. How was your day? Was it good? No, you're not disturbing. It's just that I was just uh looking at two different things. It wasn't you. It was me. Uh, okay. No, you don't. So um, you can go to Google Colab over here. You just write Google Colab. You just log in your Gmail account, and then you can also do it anywhere, like on even on a shitty laptop. It doesn't really matter. You can do it over here. You don't need to have a good laptop for practicing. This can run because this is running on browser. This can run on your laptop, your iPad, whatever. Any as long as you have a keyboard, this will work. There we go. Nah, it's fine. It's perfectly fine. I mean, I shouldn't be gatekeeping this information, right? And I'm always open to helping people out when they're starting things out. It's always nice to have like a path to know how to go or enter this career. Um, when I was starting out, I didn't know most of the things, so I was just um, looking at random stuff, and then slowly, I started understanding. Okay, maybe this path is much better, and then whenever someone starting out, I just tell them that hey, these things are pretty good. And right now, I was talking to this really nice guy on Twitch, and he was explaining me, or he was suggesting me really nice suggestions in my AI code, and I was learning from him. So I'm just, you could say it's like a butterfly effect. Someone does good for me, and then I return that good thing to someone else. Okay, the specific mean and the standard deviation values mean 0.485, 0.456, 0.406, standard deviation 0.22 are not actually in the original Alexnet paper. Instead, they're modern industry standard derived from the entire ImageNet training set and popularized. Okay. They calculated the mean RGB value for each pixel from the entire data. Well, where does the modern values comes from? The values that you see, researchers analyzed roughly 1.3 images. Okay. I do not have any course. I didn't have enough time to make a course on this. Maybe I'll make a course. Um, so first I need to know again, like, what is your experience? Do you know any programming language at all? Do you know Python at all? So let's start there first. Is there uh I think it's really a good practice that I should also write whatever the new things I was learning. I'm just learning. Okay, then I would say first thing that you have to do is learn Python. Learn a programming language. Um, v- to be honest, I would say learn C++ plus plus first and then do Python because C++ plus plus is a little bit difficult. Um, but it teaches you a lot of really good things which Python ignores, and those are very important concepts whenever you're doing computer science. They're also useful when you do AI as well, but Python does it for you. So people often recommend that you should learn Python first. But For me, I learned C++ first, and then I learned Python within a week. That's just how it is. If you do the hard part first, Python is very easy to learn. So I would suggest you to learn C++. Once you do that, then you learn Python. Once you do that, then we can talk about how you will be learning AI. But don't jump. These are the first two things that you need to learn, then you can do AI. Sure. Yeah, yeah. I mean, take your time. You don't have to rush or anything. Take your time. Bum, bum, bum. Bow, 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 bow. Do, 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 do. Oh yeah, you were converting it from 256 pixels to 0 and 1. So okay, can we connect anywhere? You can connect me on LinkedIn, I would say. I think that's the other. I mean, you can always like message on YouTube, and then there's just LinkedIn, I think, for now. Yeah, blah, blah, blah. Okay, WhatsApp or Instagram? WhatsApp or Instagram? For now, no. Because I have to create another Instagram account because I need to stop spammers, to be honest. So for now, I would say I can't give you much on the um, social media for now, unfortunately. Sorry about that. Okay, so you're applying normalization. Pow, pow, pow. Pow, pow, pow. All right. Renown values and Pytorch community for ImageNet dataset. I will not disturb you. I will come after learning C++ and Python. And yes, if you want, then we can connect. Sure, that would work. That would work. I mean, like when you say disturbing, like right now, we can talk, we can communicate. It's perfectly fine. It's just that I'm a little bit hesitant right now to share my social media. But yes, maybe when you are after a month or whenever, like take your time. You learn C++, you learn Python, you come back. Hopefully, I'm still streaming by then. I hope on streaming, or you can we can then see, maybe I can then connect with you. That would be nice. Okay. So renown values in the Pytorch community for the ImageNet dataset. So that's why we're doing that. then we do the random resize crop and oh, I mean, you can't lose me from you. I mean, you can subscribe to me on YouTube and you can always message me on any of the videos. Like, I have multiple videos, and think you can just message me um on any of the YouTube videos, and I always get like a notification, and like I always read the comments. So don't worry, you won't lose me. It's fine. Don't have like they say FOMO, fear of missing out. You're not if you're not missing out on anything. How old are you, by the way? Not this. 21. Good. Nice. Randomly change brightness by 20%, contrast by 20%, saturation by 20%. Okay. Um, subsi- Substitute for PCA augmentation. Augmentation. Okay. So that is the data augmentation part. Uh, pow, 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 pow. Let's take a small break. And now I will stare at my screen. Yeah, I've been like streaming, I think it's like 2 hours and 30 minutes right now. And I was just going back and forth with like reading the research paper, implementing it, and then I was talking to another person, like Ducci. Um, he's my first Twitch follower, so I was talking to him. So I'm a little bit exhausted right now, so I'm taking a little bit break. Why you don't upload video from 8 months ago? Because I completed because what I used to do was I loved teaching a lot. So I used to do my bachelor's, and what sorry, when I was doing my bachelor's, I was uh learning a lot of these different courses, and what was end up happening was I was explaining the same thing to my friends over and over and over again. So to one friend the same thing, and then to another friend the same thing, and to another friend the same thing. And then after I completed the course, I would forget these whatever I had learned. So I started making videos. And then what I would do was I would watch them again. So it helps in like revision whenever I forget something. Yeah, I even do look at some of my videos again while I'm studying my masters. There are some useful topics that I still use. And after bachelor's, I made a lot of videos for my master's course, but they're so niche, they're so specific, and they're more related to robotics that the general audience won't find it useful. So they're still there, it's just marked as unlisted. And to be honest, like making a video is, I mean, it consumes time. So I was like, let's leave it. I'll start streaming where um I'll just do my work, I'll learn my stuff, and then yeah, like that. If I maybe have a little bit more time, then I might make very condensed versions of videos where whatever I achieved in the stream or whatever I learned, I will make like a small video, uh, which will also help as like a recap for me. So in short, you could say I got lazy and I didn't want to put on so much work on making videos. Also, I kind of like lost a little bit of motivation to make videos, but now I'm back and strong. I have faith in the streaming um, strategy or the streaming model. Um, to be honest, you are joining my stream and I'm doing something related to education or something related to studies, which to be honest is not that exciting because you could watch a movie, you could watch a series, you could watch some gaming video or not a tutorial but gaming video. You could play some video games instead. So at least you're here, um, and you're listening to these things, so that's pretty nice. So you are not lazy, um, because you are trying to learn, and that's really nice. And I'm assuming you're doing your bachelor's in computer science or informatics. I think that's what they say. Computer software engineering. Okay. That means um that means what? Um I don't know because in my country when I was doing, I mean, I was in computer science and my friends, some of my friends, they were in computer software engineering, or in short we just call it software engineering, and they would study some courses which were um just really related to software engineering, and there were some courses which we learned in computer science which were better than it. So um yeah, don't be restricted by what you're learning in your course. um when you get free time, so it's computer science engineering, then it's fine. One recommendation that I'll give you, so if you don't know a programming language, then that means you're just starting out, I think. I think maybe you just started out your bachelor's right now, because I think you're roughly 21. Yeah, you must be like just starting out your bachelor's. Yeah, figures. You are, as what we used to say in our university, a freshie, because you are fresh. You are just starting your um career, or you could say um your field. Uh, some good recommendation that I'll tell you. Yeah, fresher, freshie. Some really good advice that I'll give you is don't um don't hate the subject. There will be times when you are studying some courses which will be really, really frustrating and really, really annoying, and sometimes you won't even understand what you're studying. Sometimes it will take you more time to understand something than your friends and your colleagues, and that's perfectly fine. But always have fun. This is, I know, something very cliche, right? But the more fun you have, the more easier it is to learn something. So if whenever in doubt, you're like, hey, why am I studying this particular thing, right? What's the use of this? I know I'm not even going to do this. So, for example, let's assume integral calculus, right? You don't like it. What's integral calculus? When you study AI, I mean, as if you study masters in AI, there are places where you're doing integration in calculus, and you're like, oh, now it's important. There are a lot of things. There were some stuff which I studied in my bachelor's, which was like, hey, I'm never gonna like study this. I'm not even gonna use this. So, for example, um, maybe you're using Windows right now as your main operating system, or you're using Mac OS. I don't know which one you're using. And there will come a course, maybe, where they will teach you Linux. And I was like, ah, man, I'm going to be an AI engineer. I really don't care about Linux whatsoever. Or I I will always use Windows. I'm not gonna do something like system administration or whatever. I don't need to know Linux. Linux is like pure programming. I am like a programmer, but I'm not that kind of a programmer. And then 1 year after, I find out that 80% of your entire AI community works on Linux. And this has happened to me multiple times where I thought that something that I studied in my bachelor's is not going to help me, and it actually comes back. So whatever you study in bachelor's, whatever it is, um, everything's important. It will help you out sometime in the future. Your bachelor course is designed in such a way that that's like the foundation that you need in any career related to computer science, may it be AI, may it be cloud, may it be web development, may it be game development, may it be mobile development, it doesn't matter. Whatever you're going to study in bachelor's, it's always important. Always. All right, so let's start with the data loader. So for this, still waiting on the data set. Still don't have my data set yet. Let's wait for the dataset to download. Okay. Nothing new on the. It's very tough future in CSE. Um, I'll be honest. It's tough everywhere. It doesn't matter. There is no easy job. There's because there are people everywhere. So it doesn't matter if it's computer science, or if it's AI, or if it's game development, web development. It doesn't matter. Everything's tough. Even odd jobs. Doesn't have to be computer related or business related. Even the odd jobs. Everything's tough. That's a harsh reality. All right, so that means I will basically use my um, loader like this. So I will create uh, so I give my training directory over here. Let me just do no. Let me do this as wacha 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 wacha. The training directory goes here. The testing directory, the transforms will go there. Batch size, number of workers. So this entire thing comes above there. And I should be documenting all of this. So let's create Notion. And I think it will be a good practice that from this point onwards, um, I will start um, when I'm about to end the stream, whatever I learned in this stream, I'll write it down on Notion so that I remember what were the key points that I um, learned. Da 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 da. Notion. So let's create a new page. Let's call it Alexnet implementation. So the first thing is the discrepancies in the original paper versus the modern tech modern paper. So in the original paper, the kernel size is different. So let me give a reference to the image, Alexnet paper. In the modern one, it's different. So use this GitHub repo and the one parameter parallelization trick. Parallelization. I don't know how to spell parallel. Parallelization. Yep, I was right. Parallelization trick. It's different. And then we add the reference here. Da 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 da. Da 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 da. Pew, pa pow, pow, pa pow. That's one thing, and that's another. I've become so numb. Okay, so that's one thing that I learned today. Then, when I was implementing it, I asked myself, why adaptive average pool was used? Why adaptive average pool was used, right? And the answer that to that question is because um, because of this, and it didn't do the right job. I'll do the styling afterwards. So that was one question, like why did they use adaptive average pool? Then the other question was, so that was the first discrepancy. The other discrepancy was they don't use LRN, and the reason why you use um, why don't or why is the modern method, not paper, method not using LRN? And the answer to that one, because it doesn't help that much. Uh, then the next question was um, this thing that I learned today. So um, oh my god. The next thing was who's the muffle man, the muffle man, the muffle man, the muffle man, the muffle man. Um, what was I doing? Server, monitor, session. Why use normalization mean of 0.5 of 0.4? What was it again? And not 0.5 because it is renowned in the research paper world. Feel like not too much viewers today. It is pretty dead. Pretty dead. And I'm also on the 3 hour mark. So I should stop now and play a little bit of video game. Sorry, excuse me. Which game? Okay. So there are 4 games. Um, there is this one. So I don't stream my gaming stuff on this channel. I do it on another channel. I can give you the link to that if you want. Um, I'm playing this game called Sword of the Sea. It's a very short game. It's a very, very beautiful game. So this is the one. It has um, very beautiful graphics. It's open. It's not open world, but it's like an exploration game, and it's so calm and relaxing to play this. And it's like in total, I think 6 hours long. You can complete this entire game in 2 hours, but most of the time I'm like taking pictures. So they have like a photo mode inside there. So I'm making or taking photos in the game, and that's why it's taking me so long to play. I mean, complete this. So that's number one. The second game sometimes I play is Overwatch because my friends are playing Overwatch, so I just play Overwatch with them. Like sometimes multiplayer game. I am once I'm done with this Sword of the Sea, I am going to start with Resident Evil. I've never started the Resident Evil franchise. Resident Evil 9, the one with that just came out, was pretty good. So I'm gonna start the franchise, and I'm gonna start with 2, 3, 4, whatever. Like I think I'm gonna play 4 games, so I'm gonna stream it over there. So that's the third game, and the fourth game is Elden Ring. So it depends on my mood, what I'm feeling, and then I'll play that game. The YouTube channel for the other one, I still have to decide what the name is for that YouTube channel, but where is it? It's fairly new, actually. This is the channel name. So I can also show you as well. So there's this one. Um, yeah, like it's very new. It's very, very new. So I'm probably gonna play this in a little while. Ah, thank you so much. Means a lot. Thank you. Because it is right now in the research paper world. I hope that the stream is okay. The audio is okay, and also um the resolution is also okay. Like you can also read what I'm writing down. I'm not sure um, if that is the case or not. Okay, where was I again? Ba, ba, ba. So I did learn this, and one more thing that I learned today. All okay. We have been approved by Sami. That is good. Sami approves. That's good. Also, I was wondering, how did you encounter this channel? Because I don't know if you're on laptop or are you on mobile, because this is like a, yeah, I don't know how you discovered this channel, by the way. So I'm a bit curious about that. Uh, Now comes this part. Let's do, or let me just write this. Suddenly, I found it in my YouTube feed. Okay, so I'm guessing when you open your YouTube, it's like showing you videos, and maybe then it showed you that my channel is live, I think. So, okay, that makes sense. Because on the other channel, the gaming one, I'm trying to see if I can grab or, yeah, grab people in the video shorts. So, um, in my YouTube channel, you'll see that my entire screen is not being broadcasted. It's just like a vertical screen. So when you're looking at shorts on YouTube, then you might find my channel over there. So that's a little bit difference, or like a small experiment that I'm doing. Yeah, and I'm also like really shocked that I am getting any views at all, because I started this channel after 8 months. Yeah. Um Technically, uh I also want to do my own editing, because I want to learn how to edit stuff. Plus, I do um yeah, I'm pretty much doing everything for free, and I don't have money to afford anything right now. I am very early in my streaming and gaming channel. I am not even, I don't even care about, at this moment, I don't even care about um whether these things are successful or not. Right now I'm just like, hey, I'm doing something, people can come and talk to me, I can pass a little bit of time as well. And yeah, it's more about like talking to people right now, spending time, connecting. Pa 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 pa. Let's delete this entire thing. So case one. So what I accidentally did was I did this thing, and then over here I did this, and then I got an error because flatten flattens the neurons with dimension equals to 1, which means that it thought that 3 by 3 flattens the dimension with 1, and your model always assumes that you give a patch size. So what happened was 3 by 2 to 4 was when you reach this layer of adaptive average pool with the current random tensor the shape is 250 256 by 6 by 6, and when you apply flatten, it only flattens 6 by 6, so that means it becomes 256 by 36, and this doesn't matches this thing. Solution: always add batch dimension. So when I did this, now I got 1 by 256. Now I got 256, and then I got 6 by 6 after adaptive average pool, and now when I flatten I get 4096. So the matrices matches. Maybe I can also link my own YouTube link over here where I was able to discover this. So was it this one? I didn't even realize that I've done 3 streams now. Or maybe this is like my 4th stream or something. So it was yesterday's stream that I did. So I'm just going to link my stream here. And let me give the time. So the time where I discovered this was roughly around 1:36 and 38. So in future, if I don't remember what this thing was or what the solution was, I can always look at my previous stream at this timestamp and I will be like, ah, that's how I did it. And I can also link today's stream as well, but I'm not sure I have to either wait for it. No, I don't have to wait for it. Perfect. Then I can also give attach today's stream as well, and that will also be helpful. No, my mouse died. I have to charge my mouse. Let me see if there is anything on Twitch. No, nothing on Twitch. Pa 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 la pa pa. So the time for this one was damn it, I don't know what's the time because it's the other way around. So it's 1 hour. Oh no. Yeah, I'll have to do this afterwards. Which site is this and why for it? So basically, this is Notion. This is used to create digital notes. So maybe you write something down on your notebook, on your register, and 5 years later, you don't have your notebook anymore. So you create digital notes. And Notion is a really good website where you can create your digital notes. So I'm like, if I ever want to understand how I basically implemented Alexnet and what were the things that I learned, I'm writing my notes down over here. And then I can look back to it and be like, ah, that's how I implemented it. These were the problems that I faced. And this is actually pretty good because when people are recruiting you for jobs, they don't care about results. They're more concerned about when you encountered a problem, why was the problem occurring? And two, how did you solve it? That's more important. So I'm documenting everything that I'm learning. I'm like, hey, why did this not work? Because of this. What mistake I made? I made this mistake and I fixed it like this. Then this is the video where I learned how I fixed it. So that's why. Palapapa, palapapa, palapapa. Looks like I have to take another break because my mouse is dead. And I'm gonna take another break because where are you from? I am from Pakistan, but I am currently in Germany doing my master's in AI. Yeah, I did my bachelor's from Pakistan and then I came here for my master's. I was not always in AI. Um, I started my stuff in uh, I was originally going to be a game developer, so I would like make games. I have made games a lot. Um, I think I have a website where maybe I can show you uh, the stuff that I created. I created a new game, another game, like um, in in my masters as well. I have to create a post for it. Lawson dot version dot app. Was this the website name? is someone else's app. Uh, Wait, let me see. Pa, 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 pa. Where's my profile? Profile, profile. Do I have my portfolio? Yes, there it is. This is a portfolio I made. I mean, website I kind of made back in my bachelor's. So there's an AI mode. Yeah, right now I haven't uploaded any of my games. I think I made two games. One one is I can show you. So one is this one. It's called Call of Objects. Um, I haven't uploaded the file, so you can't play the game, unfortunately. So this is a game that I made. The mouse is not working. Oh, it's not my mouse. This was an Android game. I haven't uploaded this on Play Store, whatever. Um, but yeah, this was like a mobile game that you could play. So that's one. Then I also did some work in virtual reality. So you wear that virtual reality glasses, and then um, yeah, something like this. So you wear the virtual reality glasses, and then you can play like this gun game type simulation. Um, and there's another one. There's a third one which I made right now. That one, I haven't made a video on it. I will make a video very soon, and then I will upload. And possibly you can play that game online, but I just have to take out the time to upload it and let everybody play it. Okay, I will be right back. I will pin this message. I have to take a short bathroom break. So we'll be back taking a short bathroom break. Break. Let me do this as pin and wacha and wacha and All right, so for the implementation of Alexnet, I have created a rough skeleton. I was able to um, understand a lot of different concepts. I haven't completed it yet. Um, Maybe in the next stream. I'm not sure if I'm gonna do it tomorrow or if it's going to be day after tomorrow. But hopefully in the next stream, I'm going to um, because I was also waiting for the dataset to download. So in most probably in the next stream, I'm going to download the dataset, not download it, but use the dataset, put it in the data loader, and then train the model. So hopefully, I think in the next stream, the entire AlexNet will be completed, and then after that, we are going to look at the project, um, the other project, and yeah, um, we are then going to see. I think the next research paper will be ResNet, but I will like decide it afterwards. So yes, I'm going to now close the stream. It's been 4 hours since I've been streaming. I'm really tired now. So yeah, if you want to have a normal conversation or you just want to chill while I'm implementing some AI models, then you can feel free to join me. You can turn on the notifications so it like lets you know when I'm streaming, because unfortunately I'm not streaming at one fixed time, so I'm sorry about that. But if I am streaming, you will know that through the notification bell. And yeah, I'll see you guys in the next stream. So bye bye. Pa, pa, pa. Stop streaming and